At the end of this video, you should be able to list the 4 quantum numbers and describe their significance, and relate the number of sublevels corresponding to each of an atom's main energy levels, the number of orbitals per sublevel, and the number of orbitals per main energy level. Chapter 4, Section 2, Atomic Orbitals and Quantum Numbers. In the Bohr atomic model, electrons of increasing energy occupy orbits further and further from the nucleus. According to the Schrödinger equation, electrons in atomic orbitals also have quantized energies. An electron's energy level is not the only characteristic of an orbital that is indicated by solving the Schrödinger equation. In order to completely describe orbitals, scientists use quantum numbers. Quantum numbers specify the properties of atomic orbitals and the properties of electrons in orbitals. The first 3 quantum numbers result from solutions to the Schrödinger equation. They indicate the main energy level, the shape, and the orientation of an orbital. The 4th, the spin quantum number, describes the fundamental state of the electron that occupies the orbital. As you read the following descriptions of the quantum numbers, refer to the appropriate columns in Table 4-2 on page 104 of your text, or on the screen now. Principal quantum number. The principal quantum number, symbolized by n, indicates the main energy level occupied by the electron. Values of n are positive integers only, 1, 2, 3, and so on. As n increases, the electron's energy and its average distance from the nucleus increases, as is also shown in figure 4-12 on page 101 of your text, or on the screen now. For example, an electron for which n is equal to 1 occupies the first or lowest main energy level and is located closest to the nucleus. As you will see, more than one electron can have the same n value. These electrons are sometimes said to be in the same electron shell. The total number of orbitals that exist for a given shell, or main energy level, is equal to n squared. Angular momentum quantum number. Except for the first main energy level, orbitals of different shapes, known as sublevels, exist within a given value of n. The angular momentum quantum number, symbolized by L, indicates the shape of the orbital. For a specific main energy level, the number of orbital shapes possible is equal to n. The values of L that are allowed are 0 and all positive integers less than or equal to n minus 1. For example, orbitals for which n is equal to 2 can have one of 2 corresponding to the value of L. L is equal to 0 and L is equal to 1. Depending on its value of L, an orbital is assigned a letter, as is shown in Table 4-1 on page 102 of your text, or on the screen now. As is shown in figure 4-13 on page 102 of your text, or on the screen now, s orbitals are spherical. P orbitals have dumbbell shapes, and d orbitals are more complex. The f orbitals and their shapes are too complex to discuss here. In the first energy level, n is equal to 1, there is only one sublevel possible, the s orbital. As mentioned, the second energy level, n is equal to 2, has 2 sublevels, the s and p orbitals. The third energy level, n is equal to 3, has 3 sublevels, the s, p, and d orbitals. The fourth energy level, n is equal to 4, has 4 sublevels, the s, p, d, and f orbitals. In an nth main energy level, there are n sublevels. Each atomic orbital is designated by the principal quantum number followed by the letter of the sublevel. For example, the 1s sublevel is the s orbital in the first main energy level, while the 2p sublevel is the set of p orbitals in the second main energy level. On the other hand, the 4d orbital is part of the d sublevel in the fourth main energy level. Magnetic quantum number. Atomic orbitals can have the same shape but different orientations around the nucleus. The magnetic quantum number, symbolized by m, indicates the orientation of an orbital around the nucleus. Here we describe the orbital orientations that correspond to various values of m. Because an s orbital is spherical and is centered around the nucleus, it has only one possible orientation. This orientation corresponds to the magnetic quantum number of m is equal to 0. There is therefore only one s orbital in each s sublevel. As is shown in figure 4-14 on page 103 of your text or on your screen now, the lobes of the p orbitals can extend along the x, y, or z axis of a three-dimensional coordinate system. There are therefore 3 p orbitals in each p sublevel, which are designated px, py, and pz orbitals. The 3 p orbitals occupy different regions of space and correspond, in no particular order, to the values of m is equal to -1, m is equal to 0, and m is equal to +1. There are 5 different d orbitals in each d sublevel. See figure 4-15 on page 105 of your text or on the screen now. The 5 different orientations, including one with a different shape, correspond to the different values of m is equal to -2, m is equal to -1, m is equal to 0, m is equal to +1, and m is equal to +2. There are 7 different f orbitals in each f sublevel. As you can see in table 4-2 on page 104 of your text or on the screen now, the total number of orbitals at each main energy level increases with the value of n. In fact, the number of orbitals at each main energy level equals the square of the principal quantum number, n squared. What is the total number of orbitals in the third energy level? 9. Specify each of the sublevels using the 3 quantum numbers you've learned so far. Spin quantum number. Like Earth, an electron in an orbital can be thought of as spinning on an internal axis. It spins in one of 2 possible directions, or states. As it spins, it creates a magnetic field. To account for the magnetic properties of the electron, theories of the early 20th century created the spin quantum number. The spin quantum number has only 2 possible values, +1/2 and -1/2, which indicate the 2 fundamental spin states of an electron within an orbital. A single orbital can hold a maximum of 2 electrons, which must have opposite spins.
The principal quantum number n is a positive integer describing the energy level of the electron. For example, an electron for which n equals 1 occupies the first or lowest main energy level and is located closest to the nucleus. The angular momentum quantum number L can be any integer from 0 to n minus 1 and describes the shape of the orbital. The s orbital can be represented by a sphere. The p orbital can be represented by a dumbbell shape. The d orbital is primarily shaped like cross dumbbells, but can also have a 5th dumbbell ring shape. The magnetic quantum number m can be any integer from -1 to +1 and describes the orientation of the orbital. Orbitals run along the x-axis, the y-axis, and the z-axis, as shown in this p orbital. The spin quantum number has only 2 possible values, +1/2 and -1/2, which indicate the 2 fundamental spin states of an electron in an orbital. A single orbital can hold a maximum of 2 electrons, which must have opposite spins.
At this point, you should be able to list the 4 quantum numbers and describe their significance, and relate the number of sublevels corresponding to each of an atom's main energy levels, the number of orbitals per sublevel, and the number of orbitals per main energy level.